Welcome back, everyone, to another week of physics. So, for part 5, we're gonna take everything that we have learned so far about series and parallel circuit rules and apply it to a circuit where you use series connection and also parallel connection. So, before we move on to the whole circuit, let's keep it simple first and talk about the resistors only. Now, resistors can be connected in series and parallel, and you can have different combinations like the one shown here. So let's do the first one here. Now we have two resistors in parallel and then one resistor that is in series to those two parallel resistors. I'm going to call this resistor A, this one is resistor B, and then this one is resistor C. You cannot simply add them all like in a series circuit because there are some parallel resistors here. So what you want to do first is you want to find the overall effective resistance of these two resistors. So that's what we're going to do first. So we're going to find the overall resistance of A and B. And in order to do that, because they are parallel, we have to use the formula of resistors in parallel. So it's this one here. 1 over the total is equal to 1 over R1, which is in this case is RA, plus 1 over R2, which is in this case is RB. It's just the same, but I'm just using different notifications so that we don't get confused. So the first resistance A is 5 ohm. The second one has a resistance of 10. So if you add these two together, you will get 3 over 10. Now you don't stop there. You then have to flip this around in order for you to just get the effective resistance of A and B, and that is equal to 10 over 3, which is basically equal to 3.33 recurring ohm. Okay, so now that you know the effective resistance of the two resistors in parallel, you can imagine this circuit as being like this. So instead of having those two resistors in parallel, you can imagine those two parallel resistors A and B being replaced with a resistance of an equal effective value, and that is 33.33 ohm, and resistor C is there. Now if you imagine it like that, you can see that now you have a series circuit. So the next thing to do is you can add these two together. So if you want to know what the overall total resistance is of these two, that is equal to the resistor, let's call this is AB now, resistor 1, which is resistor AB, plus resistor 2, which is resistor C. Resistor AB is 3.30 ohm and resistor C is 10, and that will give us 13.33 ohm, and that is the total effective resistance of the first circuit here. Let's do the second example. You have three resistors. These two are in series, so I'm going to call this A and B, and then this one at the bottom here is in parallel with the two in series. So which one do we do first? Do we do the parallel one first or do we do the series one first? In this case, you can do the series one first. You can find the total resistance of A and B. That's because you cannot add them in parallel because the series resistors are in the way. So let's find the total resistance of A and B first. And for this one, because they are in series, you can just add them together. So resistor 1 is resistor A, resistor 2 is resistor B. Add them together and you will get 15 ohm, right? So then you need to do a bit of imagining in your head. These two resistors in series, you can replace it. So this is resistor C, that is 10 ohm. The two resistors A and B that are in series, you can basically imagine that you are replacing it with a resistor of equal value, and that is 15 ohm. So we're going to call this resistor AB. Okay. Now you imagine it like that, you can see that these two single resistors are in parallel. So you can now add these two using the parallel formula. Then you can find the total resistance, which is 1 over the first resistance, which is resistor AB, plus 1 over R2, which is resistance C. And this is 1 over 15 plus 1 over 10. And this will give you 1 over 6, but that's not done. You have to flip this around. And the total resistance of these three resistors, or the effective resistance of these three resistors, is equal to 6 ohm. Now, how do you do a circuit where you have a series and parallel connection, like example 5 here? So the question reads, the battery in the circuit has an EMF of 6 volts and negligible internal resistance. So that means you can just ignore the resistance in the battery. The battery doesn't have resistance. Calculate the combined resistance of the two resistors in parallel. So in this question is quite easy because the question guides you what to do. So in this case, we want to find the resistors in parallel. We merely have to use the parallel formula here. R1 is equal to 2, R2 is equal to 4, and that will give us 3 over 4, or RT is equal to 4 over 3, and that's equal to 1.33 recurring ohm. And that's to 3 significant figure. Now let's find current I1 from the battery. So current I1 is this one here, and this is what we call the total current or the main current. So whenever you want to find the total current, you have to use the total voltage and the total resistance, and also this formula here. So you have to use the formula of R is equal to V over I, but rearrange this to make I the subject of the formula. So now the formula becomes I is equal to V over R. And let's put down a small t, which stands for total, because we want to use the total of everything in order to find I1. The total voltage, what is the total voltage? That is basically the EMF, so that's 6 volts. The total resistance, how we can find the total resistance? We have to consider the final resistor here. We know that these two parallel resistors here have the effective resistance when combined together of 1.33 ohm. So, and these two are in series with this one. So if you can imagine, you can replace something like this. In order to find the total resistance, you can simply add these two together. So it's basically 1.33 plus 10, and that's equal to 11.33. So the total resistance is 11.33, and that will give you a current of 0.530 amps, and that is to 3 significant figure. Next, find the potential difference across XY and YZ. So XY is these two resistors here, and YZ is only this resistor here. Let's do the easy one first. We want to find the voltage across YZ. We gotta use the formula of R is equal to V over I in this case, and rearrange this to make V the subject of the formula. Now let's put small yz to denote that these values are the values for point Y and Z. Now, what's the current at point YZ? As you can see, the current I1 splits up at this junction, and then when it goes back to junction Y, it forms back to become I1. So remember the first rule of the parallel circuit for current: when it reaches a junction, it can either split up or add back. So in this case, the current at YZ is basically the current at I1, and this is equal, we calculate it to be 0.530, and the resistance at this point is 10, and that is equal to 5.3 volts. Now let's do the one for VXY. There are several ways of doing this. One is using the parallel circuit rule, and the other is using the formula, and I'll show you both. So let's do the first one here. So this is the first way of doing it. What you need to realize is that the voltage here is 5.3 volts, and the voltage here is 6 volts, so that's the EMF. What is the voltage for these two parallel circuit here? Now, if you imagine these two parallel resistors as one resistor, that is the total effective resistance of those two we calculated before, and you will see that this one has a voltage of 5.3 volts. The EMF has a voltage of 6 volts. What is the voltage across the other resistor? This is the series circuit rule for voltage. The voltage from the EMS is shared between the components that are in series. So if you want to find the voltage here, it's basically 6 volts minus 5.3 volts, and that will give us 0.7 volts. Okay, so that means because these two are parallel with each other, and you have to remember your parallel circuit rule for voltage, they have the same voltage. So this is 0.7, this is also 0.7 because they are parallel. But between X and Y and Z, okay? Now the second method, I'll use a different color pen. We want to find Vxy. So we have to use V is equal to IR. And let's put in xy to show that these two values are for the xy point. And in order to do this, again, you have to imagine the two parallel resistors as only one resistor. So you combine those two together and imagine them as one resistor. And this is 1.33 ohm, and the other one is 5.3 volts. Okay, and we know that the main current I1 is equal to 0.530 amps, and that is also the current. If you imagine the circuit to be like this, that is also the current flowing through the combined resistor of the resistors in parallel. So now that you know that, you can use that to calculate. So the current that is going through point XY should be equal to the main current, which is 0.530 times the total resistance, which is 1.33 ohm. And you can calculate this to be all the same 0.7 volts. Okay, so you can see both methods give you the same value. If you like to use the method that is mostly knowing about the circuit rule, you can use method 1. But if you like the method where you use the formula, then you use method 2. Either way, it gives you the same answer. D, you are asked to find the current I2 and I3. Again, there are two ways of doing this. The first way is using the formula R is equal to V over I, this formula here, and you make I the subject of the formula. All right, so I2 is equal to V2 over VR, and I3 is equal to V3 over R3. So if you want to find I2, you have to use the voltage at the 2 ohm resistor, which is 0.7, we know from our previous question, and resistance 2, which is 2 ohm, and that will give you 0.35 amps. I3, you can use again, V3 is 0.7, R3 is 4, and that will give you 0.175 amps. Using the first circuit rule, you can check that I2 and I3 is equals back to I1. Okay, because these two current, they are split from I1. And if you do that, you will see that they will equal back to 0.3 roughly. The second method is using I1 and the ratio between the two resistors. Okay, so you know I1, which is the main current, is equal to 0.530 amps. And when it goes to I2 and I3, this will split up. But as you can see, I3 has double the resistance than I1. Okay, so that means I3 has less current than I2 because the ratio of the resistance is 2 to 1, or in other words, 4 is double 2, so it's 2 to 1. Therefore, when it comes to the current, one is double the other. So the current that is passing through the 2 ohm should be double to the one that's passing through the 4 ohm, because when you have less resistance, you have more current. So if the resistance is half, then the current is double. So all you have to do is find out the ratio of the current that is split between these two branches. So for I2, this should be, you should do like this. So 2 over 3 times 0.530, and that is equal to 0.35 amps. And then I3 is half of that. So you can just simply half that value, or you can just use the ratio, and that is equal to 0.175 amps, roughly speaking. Okay. And so if you add these two back together, it should give you back to the total value, which is 0.30 amps. So disclaimer, when I'm doing this, I'm using the exact value for the current. That's why I can get the exact values here. Your calculations might be a bit off by a few decimal places, because you might not be using the exact value, and because we are dealing with fractions, and that's why you cannot get the exact answer. Now, this is something different. This is something extra to what we're planning to do in this video lesson. I do not know where to put this part of the topic, so I'm just going to put it at the end of this lesson here. And this is something that's called short circuit. So you probably heard of this before. So what happens during a short circuit? If an alternative route of less resistance is provided to a circuit, the charges will elect to choose the path of least resistance. Hence, a short circuit is created. So let's look at this example here. So ignore this part here. Okay, so let's say the circuit looks like this originally. So it's just a cell and a light bulb with a current flowing through it. And then something happens to the circuit. Maybe there's a tear in the wire, or maybe the wire is touching a different wire, and a different path is created because of that. So now you have another path that is created in the circuit unintentionally. So what's going to happen? So when the current goes through to this point here, the current has two choices. It can either flow straight and through the light bulb, or it can go down to this new path and bypass the light bulb. As charges, they do not like to go through paths where there is a lot of resistance. So this light bulb here has resistance, and it gives a certain resistance to the top path here. Whereas the bottom path has no component at all, nothing at all. It has a lower resistance. So as a charge, which path are you going to use? You are definitely going to use the bottom path, because the bottom path is the path of least resistance. It's very easy for the current to flow. So what the current will do is that most of the current will flow through the new path and bypass the light bulb. So they won't go through the path that is meant for them to go through. And because there's less current flowing through to the light bulb will not light up, and the circuit will not work as intended. So this is what we call a short circuit. It's basically when the current uses a shortcut that we do not intend it to use, and the circuit doesn't work. So a short circuit is quite a common electrical fault in circuits. And that's the end. So you can see when it comes to problem solving using series and parallel circuit rules, it can be quite confusing. So my tip is to always remember all 6 of the circuit parallel rules, and then make sure to label your diagram. Sometimes labeling can help you see what is the solution to the problem. And also realize that when it comes to these sort of problems, there are usually more than one solution. So there are different ways of doing it. And we also looked at what is a short circuit. And this is basically a type of electrical fault that normally happens in a circuit. In the next video lesson for part 6, we'll look at potential dividers.